Section 12.3.2 Base 26 Linearity. Let's start the investigation of linearity with substitutions based on a 26-character alphabet. This might be valuable if you are designing a mechanical or electromechanical cipher device, or if you are simulating one. Each rotor in such a machine performs a substitution on a 26-character alphabet. Begin by considering an S-box that has no key. There are multiple forms of linearity that can occur with a 26-letter alphabet, depending on how the letters are numbered. There are three ways to view the alphabet: treating the alphabet as a single sequence of 26 letters, treating it as a 12 by 13 array of letters, or treating it as a 13 by 2 array of letters. These lead to three different ways of numbering the characters: N1, N2, and N3 as shown. The discussion of these three numbering schemes uses modular arithmetic. If you would like to review modular arithmetic at this time, see section 3.6. Numbering schemes N2 and N3 follow the usual convention of using the letters A, B, and C to represent digits beyond 9. That is, they use the first 13 of the 16 hexadecimal digits. In the simplest linear encipherment, the Balazzo cipher, the key is just added to the plaintext. When the key is added to the plaintext character, in the N1 numbering scheme, it uses conventional addition modulo 26. When the key is added to the plaintext character in the N2 numbering scheme, the first digit is added modulo 2, and the second digit is added modulo 13. Conversely, when the key is added to the plaintext character in the N3 numbering scheme, the first digit is added modulo 13, and the second digit is added modulo 2. Here are examples showing how the word the is enciphered by adding the key J in each of the three schemes. If the plaintext, the key and the ciphertext alphabets are all numbered using the N1 scheme, then a linear substitution, or linear transformation, would take the plaintext character P and transform it using the key K into the ciphertext character C equals MP plus F of K, where M is a multiplier which must be co-prime to 26. F of K is any integer-valued function, and the arithmetic is done modulo 26. For example, if M equals 5, P equals 10, K equals 3, and F of K equals K squared plus 6, then C equals 13, because 5 times 10 plus 3 squared plus 6 equals 65, which is congruent with 13, mod 26. The constant M and the function f of k can be built into the substitution table. If the plaintext, the key and the ciphertext alphabets are all numbered using the N2 or 2 times 13 numbering scheme, either the first digit or the second digit or both digits can be linear. Suppose that both digits are linear. Then a plaintext character P equals A, B is transformed using the key K into the ciphertext character C equals MA plus F of K, NB plus G of K, where M must be co-prime to 2, meaning M equals 1, N must be co-prime to 13, and F of K and G of K may be any integer-valued functions. The arithmetic is done modulo 2 and modulo 13, respectively. The constants m and n and the functions f of k and g of k can be built into the substitution table. If the plaintext, the key and the ciphertext alphabets are all numbered using the N3 or 13 times 2 numbering scheme, either the first digit or the second digit or both digits can be linear. Suppose that both digits are linear. Then a plaintext character P equals A, B is transformed using the key K into the ciphertext character C equals MA plus F of K, NB plus G of K, where M must be co-prime to 13, N must be co-prime to 2, meaning n equals 1, and f of k and g of k may be any integer-valued functions. The arithmetic is done modulo 13 and modulo 2, respectively. The constants m and n and the functions f of k and g of k can be built into the substitution table. There is no requirement that the plain text and the ciphertext are numbered the same way. There can be a correlation between any digit of the plain text and any digit of the ciphertext in any numbering. Emily might test any or all of these combinations, looking for an exploitable weakness. Consequently, the designer of the cipher must test all of the possible numberings and correlations to verify that no such weakness exists, or to learn where countermeasures must be taken to prevent Emily from exploiting such a weakness. For example, you can use substitutions that have different weaknesses in alternating rounds of a block cipher. In most cases, each substitution will diminish the weakness of the other. Of course, you should test this by hunting for linear relationships between the plain text and the final ciphertext produced by the last round. If you wish to test the linearity of a substitution, you cannot apply the correlation coefficient directly. This is because all of these substitutions are done using modular arithmetic. Consider this substitution using the n1 numbering scheme. This is almost exactly c equals 2p, so it is highly linear. However, the correlation coefficient between the plain text and the ciphertext alphabets using this numbering scheme is 0.55556, indicating that the substitution is only weakly linear. The correlation coefficient should have been calculated using the following distribution, which is equivalent to modulo 26. The correlation coefficient using this numbering is 0.99987, correctly showing very strong linearity. This illustrates a difficulty of using the correlation coefficient in cryptography. You are always working modulo the size of the alphabet. To find the correct correlation, you need to add 26, then 52, 78, and so forth for the n1 numbering, or 13, 26, 39 for the n2 and n3 numberings. In the previous example, the place where you needed to start adding 26 was obvious. It was where the ciphertext numbering went 22, 24, 1, 3. That drop from 24 down to 1 made it apparent. When the ciphertext alphabet is less linear, when it jumps around a bit, it may be harder to spot. For example, this substitution has a correlation of 0.3265, moderately non-linear. When it is adjusted by adding multiples of 26, like this, the correlation becomes 0.9944, highly linear. I have used single, double, and bold underlining to show where 26, 52, and 78, respectively, have been added to the ciphertext characters. An important feature to notice here is that 26 was added to the ciphertext character 2, corresponding to plaintext 5, but not to the following ciphertext characters 21 and 25. Likewise, 52 was added to the ciphertext character 1, corresponding to plaintext 14, but not to the following ciphertext character 24. It is fairly easy to determine which multiple of 26 to add when the ciphertext alphabet is close to linear. When the ciphertext alphabet is badly behaved, it becomes much harder. But that doesn't matter. When the substitution is non-linear, that is all you need to know. It makes no difference if the correlation coefficient is 0.01 or 0.35. In either case, there is not enough correlation for Emily to exploit. Don't waste time calculating the exact value. That handles the case with no key. Now suppose there is a key. If the substitution is linear, then it will have the form d of p plus f of k, where p is the plaintext, k is the key, and d and f are integer-valued functions. The addition can be done in any of the three numbering schemes, N1, N2 or N3. In this case, the key plays no role in testing the linearity. F of k is just a constant added to the ciphertext. Adding a constant has no effect on the correlation coefficient because it just gets subtracted back out when you subtract the mean value from each list of values, the centering operation. It is easy to test whether the substitution S of k and p takes the form of D of p plus F of k. Just choose two keys k1 and k2 and take the differences S of k1 0 minus S of k2 0, S of k1 1 minus S of k2 1, S of k1 2 minus S of k2 2. If the S box has the form D of p plus F of k, then all of these differences will be equal. If you repeat that for all possible keys, then you are certain S of kp has the desired form, and you can test for linearity without considering the key.